Alright, yesterday, if you remember, I asked you to solve a couple of issues, and there was a question that I asked you, and I asked you to find the impulse response of a discrete time linear and time invariant system, which was described by a difference equation. The difference equation was something like this, as far as I remember. The numbers are not very important here. Yn plus 0.9 yn minus 1 is equal to x x n, sort of thing. Okay. So the question was, what is the impulse response, provided that the system is causal? The causalness or the causality property of this system gives you an initial condition about the states of the output. It means that initially, let's say the capacitors or the inductors are all empty. There's nothing inside them. So, could you first of all develop a methodology to find the impulse response? Did you try it? Has any of you tried? And could you find a solution to this? We will learn a lot of methods to solve this problem. And most of the time, the methods will be related to the Fourier transform of this equation, which is something that we haven't seen yet. But even for the time being, we can solve this. We can find the impulse response. Well, the way to find the impulse response is to apply an impulse and measure the response. Okay, that's what an impulse response is, right? So we will say x of n is equal to delta of n, which is equal to 1 for n is equal to 0 and 0 else, isn't it? It's just a simple unit sample in the center at n is equal to 0, and for all others it's 0. So let's apply it. And let's see what kind of an output it generates. That's the way that I was asking you. So we can say yn plus 0. Let's start from y0, okay? Because before 0 we assume that it was all zeros. That's what a causal system is. The impulse is applied in the n is equal to 0 point. And before that there is nothing. So let's start by finding what y0 is. Y0 is equal to, or y0 plus 0.9 times y. What is n minus 1 when n is equal to 0? That is y minus 1. Y minus 1 is equal to x of 0. And y0 is what we are looking for, plus what is y minus 1? 0, because it's causal. Before 0, nothing was there. So plus 0 is equal to, what is x0? That's an impulse at n is equal to 0, which is 1. Which gives us the equation y0 is equal to 1. We found one sample. Now can we proceed with y1? y1 plus 0.9 y0 is equal to x1. Let's substitute them. y1 is what we are looking for. We don't know it, we want to find it. Plus 0.9 times y0. What was y0? It was 1. So plus 0.9 is equal to x1. What is x1? 0, because it's an impulse and at 1 it doesn't show anything, which tells us y1 is equal to minus 0.9. Then y2 plus 0.9 times y1 is equal to x2, which is we know to be 0. So y2 plus 0.9 times, what was y1? It was minus 0.9. So eventually it becomes minus 0.9 squared. is equal to 0, which makes y2 to be equal to 0.9 square, 0.81. And if you proceed like this, you will see that in general yn is equal to what? The next one will be minus 0.9 cubed, and then it will be plus 0.9 to the power 4, and it goes on like that. So what is yn in general? That is equal to, first of all, there is a sign alternation. It's at one point it is plus, at the other it is minus. For even n's, it is a plus, because y0 was 1, y2 was plus 0.9 square, like that. So it is minus 1 to the power n, we can say, which makes a positive for even n and a negative for odd n. And then 0.9 to the power n as well. When n is equal to 0, it makes a 1. When n is equal to 1, it makes a minus 0.9. Or in a shorter form, you can write it like this. It is minus 0.9 to the power n if n is greater than or equal to 0. Do you remember how we are shortening this expression or this condition for n is greater than or equal to 0? What was the trick to do that? U of n. So yn is equal to minus 0.9 to the power n u of n. So if you write down this answer in the exam for this question, you will get full credits, whatever that full credits may be, 10 points, 20 points, whatever. So this is the answer. Okay? As you see, without knowing much, using just some information that is provided to you, like it's causal, and I'm asking you the impulse response, it is definitely a linear and time invariant system, because I'm giving you a difference equation. Any system with a difference equation is a linear and time invariant system. And therefore, it has an impulse response. By the way, this y of n is h of n. It's an impulse response. So we get to the impulse response. For other more complicated difference equations, it may be a little bit more cumbersome. But of course, since I have shown you an example, a simple example about how to proceed iteratively to develop the impulse response and generalize it, there is a strong possibility that I may ask you a little bit more complicated one in the exam. What could it be? It could be a second order input and the first order output, for example, like this. So the input could also have some iteration, and the output could also have some iteration. This has nothing to do with the block diagrams that we are covering. I just entered into a parentheses, and I'm giving you some hints about how to develop impulse responses. Okay? So, now, today, I want to finish this linear and time invariant business by drawing the block diagrams again, but not the discrete time systems. Now let's proceed with the continuous time block diagrams. What do we mean by that? And unfortunately, this is a little bit more complicated. It doesn't have a simple delay. It doesn't even have a simple differentiator or a derivative like this. Life would be easier if we could think of a situation like this. Instead of a delay, we have a derivative or a differentiator block, which takes the derivative of its input and produces its output. But it's not like that. We are not going to do it like this. We have to invert this. for some historical reasons, we are going to build our things using capacitors, which not differentiate but integrates and accumulates. So we are going to use the accumulators. It's just the opposite of that. We will have a derivative input going into this kind of a symbol. It's like an integral S, and the output is x of t. Okay, it's just accumulating from minus infinity up to that time instant the input signal. It's integrating. But then we have to think of converting differential equations into integral equations, because starting from the differential equations, which is analogous to the difference equations, you can only build with the top one, okay, the differentiator. But we want integrators, so you must first translate your differential equation into an integral equation, which inverses or inverts all the intuitions that you may have. By the way, this thing, what could it be? What is an accumulator? Is a system with impulse response equals u of t. Because we know that when you convolve with u of t, the unit step function, what you do is accumulation, integration. In other words, if you say x of t convolution with u of t, that would be from minus infinity to t x of tau d tau. So this is the operator that we are looking for. It's a convolution with u of t. So the integrators are small systems with impulse responses to be a unit step function. Okay? We are passing through those systems. Those are our building blocks here. Okay, that's what we are going to use. Now, how can we translate a differential equation into an integral equation? We will not deal with the initial conditions of the integrations and all those things. But, for example, if you have y of t plus a1 y prime of t, and whenever I say y prime, it corresponds to a time derivative, is equal to b0 x of t plus b1 x prime of t. Suppose this is your differential equation, and we don't indicate any initial conditions, because the initial conditions don't affect the block diagrams in general. What you're going to do is you are going to integrate both sides of the equation once, so that both sides of the equation will have a minimum of the signal itself, not its derivative, not its second derivative, not its third derivative. It will have the signal and its integrals, which will correspond to cascaded outputs of that unit step response system. So let's integrate both sides of the equation, and we are going to give a notation to that. We need to notate y prime is a simple notation for derivative. We need a simple notation for the integral, and the simple notation that the book by Oppenheim uses is something like this. It's a superscript inside the parentheses of 1. It means it is integrated once. Or it is y of t which has passed through a system with impulse response u of t. Okay? Plus a1, from the fundamental theorem of calculus, we will have y of t, which is the integral of the derivative, and that would correspond to the same signal, is equal to b0 x1 integrated of t plus b1 x of t. So we will start from here, and this is what we will try to draw. The drawing of this, how can we do that? The output, at the output we have y of t. So let's draw y of t here. Now instead of the derivative, or instead of the delayed versions, we have one integrated version. And how can we do that? Excuse me, before that we have to put all the things to the right hand side except y of t, because y of t is the output. Let's try to isolate y of t. A1 times y of t is equal to b0 x1 t plus b1 x of t minus y1 t. Okay? We have to first write these, and then y of t will be something strange. It must be equal to 1 over a1 in a big parenthesis the rest. b0 x1 t plus b1 x of t minus y1 t. Okay. So now what's going on? Now we will try. The output is y of t. In order to generate this general form of y1t, we need y of t. We need y1t, and y1t is generated from y of t using a block like this. Now, the bottom side of this block will produce y1 of t, an integrated version. That integrated version is multiplied by minus 1, because it's a minus y1t in the expression, and it is added into the input that is generated here by combining a portion of x of t is multiplied by b1, and a portion of x1, which is the integrated version of the input, by multiplying with b0. That will come from here, that input over there. And everything after the combination will be multiplied by 1 over a1 to produce y1. So now that we have the feedback portion, what is the input, the combined input using x's? That may be generated like this. We have x of t in the input, and we need its integral version as well. That is x1 of t, isn't it? This is what we have. And x of t itself is multiplied by b1, so this scale is b1, whereas x1 of t is multiplied by b0 here. So this derivative is multiplied by b0, and then they are combined to form the input. Let's combine them. That input is combined or merged with y1 of t minus scaled here, the minus scale of y1 of t, and these inputs are combined, and everything after the combination is multiplied by a 1 over a, and that would produce y of t, the output. Now here, if you compare it with your previous notes of discrete time systems, you will see that the order is quite shuffled. In the previous case, at the top we had b0, and then B1, and then B2, and then B3. It was going on like this. And if you think of this minus 1, it is minus A0, you can say. So A0 is at the bottom and A1 is at the top with a 1 over. In the previous case, it was a plus A0 here. Sorry, it was a minus A0 here, a minus A1, a minus A2, starting from top, going to the bottom. Just check your notes for that. So the order is shuffled. Why? Why did we shuffle the order? Because we didn't consider the differential equation, we just inverted it to an integral equation. So all the orders have changed. If you use a derivative operators here, then it would be B0 first and B1 next. But since an integration, the order has changed. And then, how do we get rid of one of the integrators? Again, the similar trick. We will interchange the places of these two. And when we do that, two integrals will correspond to the same operators, so we can merge them to a single integrator in the center, just like we did for the delay operator combination. So let's interchange these two portions. And how is it going to be? It's going to be the input x of t. And first we have the right hand side expression by multiplying this one with 1 over a1, and then we have an integrator, and it goes back with a scale of -1 and combined, which corresponds to the right hand side of the top figure. Then it will proceed with the left hand side, an integrator. This portion will be scaled by b1, this portion will be scaled by b0, and they will be combined to produce the output y of t. And the trick is again the same. We will focus to the central portion, and we have two redundant integrators which takes the same input and produces the same output. So why do we use two separate integrators for that? Let's only use one integrator. And then, of course, here we have 1 over a1. To the left of the output, we scale it by -1. And here we have b1, and to the right of the integrator output we scale it by b0, and we combine to produce y of t. So this is the simplified version. Well, if I ever ask a question like this, you should automatically think of minimizing the number of integrators or the number of delay elements, of course. So when I give you this equation at the top, so this is the question equation. Okay? If I ask you this and ask you the implementation in block diagrams for this question, you need to accurately and correctly proceed at several steps. The first step is to correctly translate it into an integral equation, and then from there isolate the y of t here, then come up with the top figure. If it's a 10 points question, if you somehow correctly identify the non-efficient version of the block diagram, probably you will get something like 5 points out of 10. Then if you can also interchange their places and eliminate one of the integrators to come up with the bottom figure, then you will get 10 points. Something like that. Now as you see, yeah.
onun integralini aldık. Eksi 1 ile çarpıp son topu tekrar ona ekledik ya. Yukarıda eksi 1'de de x'in integrali yok ama.
Yeah. That is true. Because you have to formulate an auxiliary variable here. Let's call this z of t. What is z of t? Z of t is z of t is z integral of t times minus 1 or minus z integral of t or z parenthesis 1 of t plus x of t divided by 1 over a. So that is z of t. That's the formula for z of t from this loop. And then the output is defined in terms of z of t as the output is z integral of t times b0 plus b1 times z of t. And that is the output. And from those two equations you must eliminate z of t in the differential equation formula. And the input-output relation must boil down to this top question formula. So it's not an isolated or individual minus 1 over a integral of x of t or anything like that. You must somehow eliminate that auxiliary variable to come up with this equation. Probably it's not immediately visible without elimination of that auxiliary signal. So you cannot say that. But I assure you that it's correct because of the linearity of these two parts. Therefore, they can be interchanged. But when they are interchanged, then a new auxiliary signal comes into the picture inside your system, which you have no idea about what it is. It's z of t, and you are using that. Okay? Now, as you see, since the ordering is from the bottom to the top, like this is A0, and that is an A1, and this is B0, that's a B1, things will get even more complicated if the orders of the input and output differential equation depth are different. For example, what I mean is this. Let's think of a most generalized system. And I'm going to write it in a most compact form, like in a summation. Both for the differential equation for the output and the input. K from 0 to n, ak d to the k by dt to the k, which is the kth derivative of y of t, is equal to another summation. This time, let's say L from 0 to m, BL d to the L by dt to the L x of t. So this is the most general form of a differential equation. At the input, the derivatives are up to m. At the output, the derivatives are up to n. In the example that I gave you, they were both 2. It was 1 actually. It was the first derivative only. It wasn't even 2. They were both 1, up to 1. So we had to integrate once to come up with an integral equation. But if they are 2, they are both 2, then you have to integrate twice, which is still something manageable. But what if one of them is 4 and the other one is 3? Let's say n is equal to 3. So these are exercises. N is equal to 3, m is equal to 2. Since they are exercises, let's keep it small, because 4 or 5, whatever, they would be huge. What's going to happen? How many times do you need to integrate? Remember that you need to integrate both sides of the equation in order to come up with an equation. Otherwise, it will spoil the equation. So, how many times do you need to integrate? You need to integrate the maximum, right? You need to integrate 3 times, both sides of the equation. And since m is equal to 2, probably at the right-hand side you will not get an x, but you will get x1 and x2 without using x. What does that mean? It means that, let's look at the top figure, this b1 here would be 0. There is nothing there. Because no x term is entering into the equation. Alright? It will be x1 and then one more integrated version, which is x2. So you are going to break this branch, b1 branch. It's not going like that. But that's a problem, isn't it? You start from here and it's like you're deleting this and you're going like this. Okay, without an x. What does it mean if you take a look at the inverted version for simplification? It means that this b1 will not be there. Don't try to write it. Okay, I'm just ruminating on it. This b1 will not be there. So the output will not be like at the top, but it will be somewhere in the middle of this system. So the system will somehow look like this. So it will not go up anymore because we have nothing here. This branch is empty. So the output will be from here. Interesting layout. Something like that. As a matter of fact, since n is equal to 3, it will be even one more. There will be another integrator. And one more summation, but the output will still be there. It will not be at the top because we have nothing coming from here. When n is equal to 3 and m is equal to 2. How about the other way around? What about n is equal to 2, m is equal to 3? Then what will it look like? Confusing. In order not to be confused, you have to rigorously write down the integral equations, come up with the necessary equations of the integral equation with the correct scales, a1, a2, a3, b0, b1, b2, etc. And what would it look like? I would claim that this thing, n is equal to 2, m is equal to 3, would look like this. The output will be from here, but there will be nothing here. Okay. Or am I wrong? Or is it something else that I've been missing? That's a question mark. I don't have example questions for these things, but a good exercise to start with this case would be, it wouldn't be n is equal to 2, m is equal to 3, but it would be n is equal to 0, m is equal to 1. That would be a simpler case, I guess. So try to think of these cases if one side is longer than the other one. By the way, I wrote, sorry, it was too fast, a differential equation like this. If both sides of the equations are the same, then the corresponding integral equation for that would be here. So let me repeat the question with both sides of the equation at the same depth. That's the simplest case. What was that? It was AK y d to the k by dt to the k y of t is equal to L from 0 to n again, bl d to the L by dt to the L x of t. Now the corresponding integral equation, if both sides of the equation are the same, would be this: 1 over an in parentheses. Why? Why do we have a 1 over an term? Because when we integrate n times, capital N times, the term with a single yt, not its integrals, but the yt itself, will have an as its scale. An times yt will be there. And it will be at the left-hand side of the equation. So in order to isolate yt, we need to multiply the whole equation by 1 over an. Just like this 1 over a1 here inside the equation. That's what it is. So we have 1 over an, and an accumulation of the inputs k from 0 to n. For the inputs I was using L. L from 0 to n, BL. It's not the derivatives anymore. It's the integrals now. X integral. What integrals do we have? The integral ordering is just the opposite of the derivative ordering. So it is n minus L of t. N minus L times integrated of t. When L is the same as n, it will correspond to x t itself. Minus k from 0 to n minus 1, because the nth term is at the left hand side. It is y of t. A k y n minus k integral of t. So as you see, when k becomes n, y n minus k will be y0. So 0 times integrated version of y is itself. It is y of t. And that y of t is here at the left hand side of the equation. So this is the integral equation that you have. And that integral equation will have a long feedback at the output. It will have a long feed forward at the input. Integrals. And when you interchange their places, that illustration you can find in the book. Please do have the book, okay? When you interchange them, the integrals will be in the center that could be merged and combined to single integrals of n integration only. Instead of 2n, n for here, n for here, we must combine them to have n integrals in the center. Those illustrations are a little bit cumbersome, and I really do not want to go into the details of these things. Fortunately, and honestly speaking, it's not a big deal either. I mean, it's not very mathematical and hard to ask complicated questions in the exam. The only complicated question, what's a complicated question? A complicated question is a candidate for an exam, okay? Since it's our duty to torture you for asking questions that we didn't do here, but still, I'm a good person, so I torture you nicely. I'm telling you that the questions that I'm going to ask will consist of 2-3 or 3-2 versions, and therefore you already know the question. So please solve them already and exercise on them. So when you come to the examination, you will be ready to answer such a case. Okay? And that corresponds to the end of this linear and time invariant chapter. The next chapter I will start in 15 minutes. So let's not start it. I'll cut the video at this point. It will be an introduction to the Fourier business, which is again something quite significant. So I'm waiting you in 15 minutes. I'll stop this right now.